So if you've noticed, I have slightly altered the title as I was looking at the title that was on the host's presentation mode before I actually was allowed control. I started realizing that simple is probably not the correct way to identify this particular talk. What I've ultimately landed upon is common fertilizer calculations. Now, there's going to be some limitations to the content that I'm going to be able to cover today, just from a time constraint. We could take this in a number of different directions. I could focus exclusively on dry products. And in fact, many of the illustrations that I'm going to provide are ultimately going to be dry materials. Or we could run down a real rabbit hole and start talking about liquid formulations. Liquid formulations is slightly more complex. And for those of you who work in the liquid world, when I say the word slightly, you recognize that it can be much more complicated than simply mixing dry materials. I'm focusing on the more common fertilizer calculations that a typical agronomist might run up against in the day-to-day execution of their job. So I think that's where we're going to spend the bulk of our time. Now realize if we start getting a lot of questions that relate more specifically to liquid blends, and all I'm focusing on is the mathematical calculations today. I'm not going to be talking about blend compatibility. That's important information, but it's a topic for a different conversation. All I'm going to be talking about are some of the basic common fertilizer calculations. You have to make sure you're on the correct screen to make this work. So what we're going to ultimately go over today is calculating material rate based upon desired nutrient rate. And what you're really going to notice is that many of the mathematical problems that we face when discussing calculations regarding fertilizer application and various fertilizer materials is we're ultimately talking about simple word problems. Well, again, I say simple. Some of these can be rather complicated, and you're going to see that as we get towards the end of this presentation. But ultimately, what we're talking about is a word problem. And I have a couple of, really, I have one particular way. It's really more of a process that I've used over the years that seems to help me stay on track with regard to, okay, am I heading in the right direction with my calculations? And then I'm also a big proponent of checks and coming back and saying, okay, if this is my decision, is there a way to check that number? So I'm going to be showing you a couple of check opportunities as we go through. I can't do it all the time because it just becomes, time becomes the limitation. My goal is ultimately to keep this to about 30 minutes. So I had that in mind when I was putting this slide set together. So we're going to calculate a material based upon desired nutrient rate. This is a fairly straightforward calculation that any of us that have tried to go and buy a bag of fertilizer from either your local co-op or a local ag retailer or even a big box store, and then you're trying to make a decision as to, okay, based upon my desired nutrient rate, how much of this product do I have to supply to achieve that desired nutrient rate? That's where we're going to start. And that's actually a really good jumping off point for the rest of the calculations, because as you can probably imagine, the complexity of these calculations are compounded. So the math in and of itself really isn't that difficult. It's just setting up your equations, and we're not going to make this very complicated equations, but you have to make sure that you're setting up your equations properly. And that's really where I'm going to be focusing the bulk of my time today. So once we learn how to calculate material rate based upon a desired nutrient rate, we're going to transition into, okay, what if we want to compare pricing of different products? How do we do that? And we have to get everything on an apples to apples basis. I can't compare price per ton to price per pound. So I'm going to walk you through mathematically how we get everything on a similar basis so that we can make sure that we have a sound comparison. And then we're going to ramp up the complexity a little bit more. And that is, we're going to transition into calculating dry blends. Again, I actually am going to show you an illustration of liquid blends as well, just because there's the math for the one that I'm actually going to illustrate makes it a little bit easier on the liquid. That's not entirely true, but it's just a little bit easier for me. And what are some of the considerations when making dry blends, specifically if you're trying to determine what your nutrient concentration is in your new blend? That's a little bit more of a calculated mathematical concept, but I'm hoping the way that it's presented, it's going to make total sense. And again, you're going to notice that as we proceed through here, there's a concept or there's a process that I'm always employing. And if you gain a comfort level with that process, it's going to make these mathematical computations a little bit easier. And I apologize, Sam, but I can see that you're bleeding through. Could you mute your microphone, please? Don't mean to call anybody out. I'm not, but I just noticed there was a little bit of bleed through. And the unfortunate thing about Zoom is I can identify who that is. So calculating material rates. Let's start here. We all, if you've had a soil fertility class, I don't recall doing this in a soil science class. You might have in your undergraduate education, but certainly if you got into a soil fertility class, we started jumping into, when you started talking about the individual nutrients and you started talking about fertilizer materials, we would always get to a point where we would, okay, if this is my fertilizer material, let's say I'm using ammonium nitrate, 3400, and my desired nitrogen rate is 120 pounds of nitrogen per acre. How many pounds of 3400 or ammonium nitrate do I have to supply to achieve that 120 pound nitrogen rate? These are those mathematical calculations. And the method that I'm going to present to you is something called dimensional analysis. There's no quiz at the end of this, so you don't need to remember that terminology, but it's really the thought process that I go through when I'm forced to do these calculations. And as you can probably imagine, as an employee of Nutrien, I set up Excel spreadsheets that automate this process for some of our sales professionals, but there's always value in understanding how to do these calculations so that if for no other reason, you understand what the math is doing to give you the desired solution, or to give you the correct solution, ideally. So we're going to start with the word problem, and I suspect that everybody loved word problems. I know they were some of my favorites when I was in high school and as an undergraduate student in a math class. So let's assume we're applying potash. We're using the 0060 form, and our desired rate of application is 70 pounds of K2O per acre. So I'm operating on some assumed conventional concepts as it relates to how we identify fertilizer materials. And one of those conventions is that when you're looking at a fertilizer analysis, specifically if we're just going to focus on NPK, I'm only going to be focusing on NPK today, but realize any of the math that I'm doing here translates to any form. And to be honest with you, you could use this for manure. Now, manure is a little bit more challenging because I have to be concerned about, is that on a dry basis? Is that on an as-is basis or a wet basis? And I have to make adjustments to my math based upon that. I'm not going to do that today. So please don't ask that question. If you would like for us to address that issue specifically, we could do another webinar or another training series. So that 60 presumes that the form of potassium that I'm talking about is the oxide form, which is again is fertilizer convention. That's what we talk about. Both phosphorus and potassium, we talk about them in the oxide form. So I just want to make sure that's really clear and where that K2O came from. So the question is, how many pounds of potash should be applied? Now, here's the way I approach these problems. And again, this is the approach which is referred to as dimensional analysis. It's the easiest way to do this is start with what my desired application rate is. All right, so I want to put on 70 pounds of K2O, and that's on a per acre basis. And you notice that I very clearly differentiated the numerator, which is the value above this dash or above this solid line, the fraction, the top part, from the denominator. And there's a reason that I do this, because ultimately what I'm going to be tracking is my units throughout my math, because all I'm really trying to do is change this from 70 pounds to K2O per acre to pounds of 0060 or potash per acre. And then in dimensional analysis, all I have to do is change units. All right, so my next process is, okay, 70 pounds. So for every pound, I know based upon this fertilizer analysis that for every pound of potash that I supply, I'm putting on 0.6 pounds of actual K2O. So that goes into my next parentheses. Now, all you really have to pay attention to is what we're ultimately trying to achieve is we want these units to start canceling out. So pounds of K2O, you notice that's in the denominator here. It's in the numerator here. If they're on opposite sides, as I carry my math out through this equation, these units will disappear. Okay, we're not going to jump into all of the mathematical reasons that occurs. If you want to really go back through that, go back to one of your fundamental math classes. Okay, but just realize for every pound of potash I supply, I'm getting 0.6 pounds of K2O. Now we just have to carry through the math. Do the math. 70 divided by, because they're on opposite sides, this is in the numerator, this is in the denominator, I have to divide 70 by 0.6, and it turns out I need 116.7. We're not talking about we're not talking about significant figures here today either. So I went in and carried it through to the tenths. I need to apply 116.7 pounds of potash per acre to achieve that desired 70-pound rate. That is as complicated as it gets. And again, I don't call this simple. This is a very common mathematical procedure that we use. All you really have to do is make sure that your units are going away. And this is why I'm a huge proponent of dimensional analysis. Now, having said that, I had a PhD student of mine when I was an academic that hated this process. And what I always told him is, if you do the math this way, you're rarely going to arrive at the incorrect answer if your units are properly canceling out. But he was still not a fan, and there was very little I could do to sway him. Now, here's a point where we can actually do a check to make sure that this calculation is correct. So we're starting back now. I know I'm putting on 116.7 pounds of potash per acre. I'm employing dimensional analysis again. I know that for every pound of potash that I supply, I'm supplying 0.6 pounds of K2O. And you may be questioning, why is this one inverted from the one up here? And the answer is, I'm trying to eliminate units. I'm trying to get rid of this pounds of potash, because ultimately I want, what is the pounds of K2O per acre that I'm ultimately supplying? So now all I have to do is multiply 116.7 by 0.6, and I'm back to that 70 pounds of K2O per acre. The great thing about all the math that we are typically employing when we're doing these calculations, there's an easy way to check it. And that's basically just reverse engineering the process. If you're following your units, you should never make a mistake. Always, always, always follow the units. And this is why I'm a huge fan of dimensional analysis. So let's proceed with another example. I'm going to start picking up the pace a little bit because I'm already 14 minutes in. Let's assume we are applying DAP that's 1846.0, and our desired rate is 60 pounds of P2O5 per acre. How many pounds of DAP is required? You're going to see this looks very similar. My desired rate of P2O5 is 60 pounds of P2O5 per acre. Again, following dimensional analysis, ultimately where I want to get to is how many pounds of DAP per acre. So I know that for every pound of DAP that I supply, I get 0.46 pounds of actual P2O5. So this looks very familiar to the previous example. 1 pound of DAP, 0.46 pounds of P2O5. These things go away, right? And so now all I'm basically doing is I'm dividing 60 by 0.46. That gets me to 130 pounds of DAP required to achieve that 60 pound per acre rate. Now, this is going to become important when we start talking about blends, because if I'm dealing with multi-nutrient fertilizer materials, a product like DAP, a product like MAP, ammonium sulfate, if I'm doing calculations that include sulfur, I have to know how much nutrient is being supplied or what other nutrients are being supplied when I make this application rate. So I went ahead and plugged this in here. So how much nitrogen is being applied when I'm applying my DAP to reach my desired phosphate rate? All right, so 130 pounds, that's what I'm supplying. Again, follow the units. I know that for every pound of DAP that I supply, I'm applying 0.18 pounds of nitrogen. And just in case you're wondering where this 0.18 comes from, this is on a percentage basis. So all I have to do is divide this by 100 to get it into a decimal. All right. So for every pound of DAP that I supply, I'm putting on 0.18 pounds of nitrogen. Again, I'm going to do this throughout the entirety of this presentation, just so you get comfortable with seeing this. Those units go away. I'm now left with pounds of nitrogen per acre. Do the math, 130.4 multiplied by 0.18, and I wind up with 23.4 pounds of nitrogen being supplied per acre when I apply 130 pounds of DAP to meet my desired phosphate rate. And again, the reason that's going to be important is when I start considering blending a product. So if I'm adding this with urea and I have a desired nitrogen rate, I have to be able to take into account the amount of nitrogen that I'm supplying here when I'm blending that with urea, because that rate will be slightly lower. And again, that will be pointed out as we get into a couple of slides down the road. Just to throw a wrinkle in here, let's do this on a liquid basis. Liquids not challenging if you're following your units. So let's assume we're applying UAN 2800, and our desired rate is 180 pounds of nitrogen per acre. And we want to determine how many gallons per acre to actually apply to achieve that rate. Okay, again, start with what we know. I want to put on 180 pounds of nitrogen per acre. All right, I know I've got 28 pounds or 28%. I almost messed that up. I've got 28% of this product is actually on a percentage basis, 0.28 pounds of nitrogen, but that's on a per pound basis if I want to make this on dry. So if I'm in dry, pounds of N, pounds of N. Now, when I asked this question, I asked specifically, I wanted you to make this conversion to gallons. So I have how many pounds of UAN per acre I have to supply to achieve this desired application rate, but there's another step. And the other thing that you have to know when you're dealing with liquids, specifically when you're making rate calculations, you have to know something that we call specific gravity. This value should be available. So if you're getting this material from a supplier like Nutrien, any of the other suppliers out there, they should be able to provide you with what the specific gravity is for that material. Just so you hear this number, water by itself, pure water, is about 8.34 pounds per gallon. All fertilizer materials, if it's got anything else in it beyond water, will have a higher specific gravity. So that's one check off the top. If this value is less than 8.34, you know that you're probably using the wrong number. You go pull that specific gravity. For every 10.66 pounds of UAN, I get a gallon of UAN. And so you notice that I can eliminate these. And now I'm left with gallons of UAN per acre. Now all I have to do is the math. 180 divided by 0.28 divided by 10.66, and it winds up being about 3 gallons of UAN per acre. For those of you who work in the liquid world, we all know that there's about 3 pounds of nitrogen. When you do the conversions, it's about 3 pounds per gallon. So if you multiplied 60 by 3, you're going to get that 180. One of the problems I have with memorizing constants, and that would be an example of a constant, is if something changes in this equation, your constant no longer holds true. So if you're using 30.00, you're going to have a different specific gravity. It's still going to be pretty close to 3, but it's not going to be exactly 3. If you understand how to do these steps, regardless of what the material is, as long as you have this information, you can recreate this mathematical calculation. Just always make sure you're canceling out your units. Let's add another level of complexity. This isn't too terrible because we're basically just building upon what we've already done. Let's assume I'm buying potash, that 0060 product. Now, don't pay attention to these prices. I did go out just to get an idea of where prices are. Actually, I went based upon last year. It's always troublesome when an agronomist starts talking prices, especially if there's individuals who are purchasers. This is just an agronomist, for the sake of math, illustrating a point. Don't go out and say the price of K2O or potash today is $350 per ton. As an employee of Nutrien, we probably prefer that, but that's not where we're at price-wise today. It's just for illustration purposes. So how much does it cost per pound of nitrogen for K2O? And I'm going to show you why this is an important calculation to be able to do, because it does allow us to make price comparisons between different products. Now, this can get fairly complicated. I'm going to try to simplify. The first one's going to be fairly simple, but there's going to be a flaw in this, and I suspect that everybody's going to see it, but that's okay. It's fine for illustration purposes. Okay, what do I know? I know that it's $350 per ton of potash. Okay, I also know that for every ton of potash, now you could make this pounds, but then I have to do another transitional step. For every ton of potash, because this is on a percentage basis, there's going to be 0.6 tons of K2O. Again, let's go ahead and cross these out. So this tons of potash is gone. So now it's $350 for 0.6 tons of actual K2O. But my specific desire was to get this into a price per pound basis. So now all I have to do is get rid of this tons of K2O, and I suspect that everybody knows that for every ton, there is a pound or 2,000 pounds. So now you look at my units, those canceled out. Now I've got $350 over pounds of K2O. Now all I have to do is the math. 350 divided by 0.6 divided by 2,000, and you wind up with a price of about 29 cents per pound of K2O. I know I keep reiterating this point, but it's critical to this. Always make sure your units are canceling. As long as you wind up with the right units in the correct positions, you're rarely going to make a mistake. Now, the only mistake you can make would be punching it in incorrectly into your calculator. Now, just to illustrate how this works, and this is not quite a fair comparison, but let's compare this to sulfate of potash. And I suspect that everybody recognizes why this is not a fair comparison. And that is because I'm also getting a substantial amount of sulfur when I make this application with this material. I'm not considering that. I'm going to show you how to do that on the next example. We're doing the same thing. It's $600 per ton of SOP. Okay, I know that I've got 0.5 tons per ton. Get rid of these. Next step, I got to get rid of the tons because I want this on a price per pound basis. The ton goes away, the ton goes away. I'm left with dollars over pounds of K2O. That's exactly what I wanted. I do the math, 600 divided by 0.5 divided by 2,000, and I get 60 cents per pound of K2O. Again, this is not a reflection of reality with regard to price. This is just an illustration of how to do the math. All right, let's make this a little bit more complicated, and we're probably going to go beyond 30 minutes as I look at the clock. Let's assume we're buying DAP, and we're buying it for $370 per ton. How much does it cost per pound of P2O5? And my suspicion is everybody sees the challenge in this math, because if I just start doing the math for the 0.46, there's also some nitrogen that has a dollar value tied to it. How do I account for that in this 370 per ton? I have to figure out a way to get rid of the value of nitrogen so that I can only focus on the phosphate fraction. This is where it's still simple math, but to get to the desired answer gets a little bit more complicated. Because the first thing I have to do is I have to exclude the cost of nitrogen or the price of nitrogen in that material. All right, so for my assumption, I'm going to be assuming urea has a cost of $350 per ton. And you're probably wondering, why would I select urea? The source isn't terribly important. The only thing to do is make sure you're selecting a pure nitrogen source only. You do not want anything in the P2O5 slot. You don't want anything in the K2O. You don't want anything in the sulfur slot. All right, you want to pick something that is just a pure nitrogen product. And the reason being, because if I have to deal with sulfur, now I have to eliminate sulfur from this cost, and it just makes everything more complex. The other sources that you could be using is ammonium nitrate, even though that's not that widely available, or you could also use anhydrous ammonia. Okay. So even though I say you could really use any nitrogen source, really you should be using a single nutrient nitrogen source, something that contains only nitrogen by itself. So what I'm ultimately coming up with is a nitrogen reference. So again, what do I know about nitrogen? I know it costs $350 per ton of urea. I know that for every ton, I'm getting 0.46 tons of actual nitrogen. All right, let's make sure we're canceling these things out. The ton of urea goes away. All right, now I know there's 2,000 pounds in a ton of urea, so the ton of urea goes away. And so I can carry out the math, 350 divided by 0.46 divided by 2,000, it's 38 cents per pound of nitrogen. All right, so now we have to do a little bit more math on this. So I know that I have 38 cents is the cost per pound of nitrogen. I know that for every pound of DAP that I supply, I'm going to be supplying 0.18 pounds of nitrogen. So this goes away. And I know that for every 2,000 pounds of DAP, I get a ton of product. So this goes away. And so now I'm left with how much price per ton is attributed to the value of nitrogen. And it turns out it's about $136.8. So $136.80. Okay, this is why this is getting so complicated. So now this is the value. This is the value of the nitrogen per ton of DAP. So now I have to eliminate this from that 370 if I want to calculate the value of P2O5. So I've got 370 minus 136.8. Now, again, some mathematical convention. If I'm subtracting things that have similar units, the units don't disappear. Okay, so all I'm basically doing is subtracting 370 minus 136.8, but it's still on a dollars per ton of DAP basis. That's important in this calculation because I've seen people make a mistake where they assume the units are gone and then they forget the next step. So I'm still dollars over tons of DAP. That's what I know. I know that if I supply a ton of DAP, I'm getting 0.46 tons of P2O5. Now I have to make my conversion. So let's just go ahead and start canceling these things out. Those go away because of that guy. Tons of P2O5 go away because I have it over here. So now I'm left with dollars per pound of P2O5, which is ultimately what I wanted. You do the math, 370 minus 136.8 divided by 0.46 divided by 2,000, and voila, you get to your solution of 25 cents per pound of P2O5 is the cost or the value or the price for the actual P in this material. Again, the math is still pretty straightforward, but because I'm dealing with a multi-nutrient source and I'm trying to identify what the value is of a single nutrient source in that product, it's a little bit more calculated how I arrive at my correct answer. So just for illustration's sake, let's just do this same process for MAP, which is 1152.0, based upon an assumption of price of 425 per ton. Again, I have to remove that nitrogen, so I would be going through the same calculations that we went through a moment ago. I know that urea costs $350 a ton. I know that it's for every ton I'm supplying, I'm getting 0.46 tons of nitrogen. I got to get tons out of there because I want this on a price per pound basis. This is going away. This is going away. 350 divided by 0.46 divided by 2,000, 38 cents per pound of nitrogen. That should look strangely similar to the previous illustration if I did my math correct, and it does. It should. And I have to go through the same process. I know that I've got 38 cents per pound of nitrogen. I know that I'm getting 0.11 pounds of nitrogen per pound of MAP that I'm supplying. I got to get this on the price per ton basis, and you do the math, 0.38 multiplied by 0.11 multiplied by 2,000, and you wind up with $83.60 per ton of MAP attributed to the value of nitrogen in that material. Same math as before, 425 minus that 83.6. My ton of MAP, this unit is going away. I know, again, now I'm just converting from pounds to tons. Tons go away, tons go away. I'm left with dollars per pound of P2O5. Now it's just the math. 425 minus 83.6 divided by 0.52 divided by 2,000 gives me 0.32. The only other thing that I will point out here, and this goes all the way back to your days of algebra, actually pre-algebra, make sure you subtract these before you start dividing, because if you just punch this into a calculator, you're going to wind up with the wrong answer, because remember, multiplication and division occur before addition. All right, so make sure that this is in parentheses or you do this math separate. Okay, that's the one thing I do want to point out. I see that error quite a bit. All right, we're already 31 minutes in, and we're just to make this a little bit more complicated. This is probably going to take us 40 to 45 minutes. I do apologize, Ad Farm, for this taking a little bit longer than desired. What if a product is priced on a per gallon basis? Let's assume we're buying a product, and you can't go buy this off the shelf, by the way. I've made this up. This is a totally fabricated product. If I'm buying something that's got a 790 analysis that's sold in a 2.5 gallon jug and it costs $15, what is the cost per pound of P2O5? Man, you read that as a word problem, you're like, man, that's really complicated. What did I say at the beginning? Start with what you know. I know that it's $15 per jug. Okay. So I know that for every jug, there's 2.5 gallons. So the jug goes away. All right. So I know from the specific gravity of this material, which should have been reported on the label, that it's 11.7 pounds per gallon. So now I'm already to 15. I'm already dollars per pound, but I want to get this on a price per ton basis so that I can make some comparisons. So the pounds go away. And so if you did this on a price per ton basis, I've got 15 divided by 2.5 divided by 11.7 multiplied by 2,000. This product equivalent basis would be $1,000 per ton, 1,025 specifically. That's pretty expensive product. Now I can actually go in and now calculate what my cost of phosphate would be. I'm not going to show you those intermediate steps to determine your nitrogen reference. You can go back to look at those slides, and we will make this available to everyone who's attending here. You can go back and rewatch the video, or you can just simply download the slide set. The slide set might be of more value because then you can just look at the equation and say, oh, I just need to plug this in here and in here, then I can get to the correct answer. So I've already gone through the process of, and I knew I would have a mistake. I forgot to take the map out of that. That shouldn't be there. So the 1,026, I calculated the price of the value of nitrogen based upon that 7% nitrogen analysis. This is where that number came from. Maybe that could be your homework, is go back and figure out how I got that $53, where I got that $53 value from. So the tons are going away, and I apologize. I knew I would forget something, and it was the map. The tons, so now I've got dollars per ton, but I want this on a price per pound basis. So the tons of P2O5, that goes away. So 1,026 minus 53 divided by 0.09, which is the phosphate analysis of this product, divided by 2,000, and it cost me $5.40 per pound of P2O5. That shouldn't surprise you. So if you went and actually bought, which I occasionally do, I shouldn't do it, but occasionally I will just run up to the local Lowe's and buy a product that's generally got some herbicide in it as well. And the price that you're spending per pound of nutrient in those products is really, really expensive. That shouldn't surprise you. Ultimately, what you're paying for is the convenience. So that's the process of comparing costs or price. Calculating blends. Again, all of this is additive. Once you understand the process that we've already been through, now we're just adding a little bit level of complexity. Let's assume we have determined that the field requires 30 pounds of nitrogen, 50 pounds of P2O5, and 60 pounds of K2O. All right, so I know what my desired fertilization rate is for the 3 nutrients. And again, you could do this for all of the nutrients if you ultimately wanted to. It just gets more complex. The math isn't any more difficult. It's just more complicated to get to your answer. Let's also assume that we're going to be using urea, MAP, and KCl as our nutrient sources. How much of each nutrient is required, and how much will the blend cost? All right. The easiest way to do this is at least from my perspective, is I always start with whatever nutrient is the lone nutrient. So if you look at our nutrient sources, urea, hey, that's straight nitrogen. If I were just calculating just a nitrogen rate, I wouldn't have to do any other steps. I would divide 30 by 0.46, boom, I get my math. And if you're wondering how I came up with that, go visit one of the previous slides. So if I just want to do the nitrogen calculation for urea, can I do that by itself? And the answer is I can't, because MAP also has nitrogen in it. So urea and MAP are linked. I can't separate the two. I can't consider urea without considering the MAP. And the same would be true if I was just trying to supply all the nitrogen with MAP. I'm likely going to oversupply my phosphorus. And that would be assuming I'm not supplying any other nitrogen source, which is not what I assumed in this example. But if you look at KCl, no nitrogen, no phosphorus. Urea doesn't have any potassium. MAP doesn't have any potassium. Hey, the potassium one is simple. This looks strangely similar to the very first example that I provided in the first slide. 60 pounds of K2O per acre. I know that I'm getting 0.6 pounds. Oh, that really stretched out for some reason. I know I'm getting 0.6 pounds of K2O. You do the math, and surprisingly enough, if you want 60 pounds of K2O, you got to supply 100 pounds of potash per acre to achieve that rate. That one's straightforward. That's why I always start with the one that's left by itself first. It's the easiest. It's the lowest hanging fruit. Go ahead and do the calculations. Now I have to go through the other two. Since MAP has both nitrogen and phosphorus and urea has only nitrogen, my next step is I want to take care of my phosphorus needs. All right. So if you recall, 50 pounds of P2O5 was my desired rate. Again, this hopefully looks very familiar. Start with what you know. I know that for every pound of MAP that I supply, I'm getting 0.52 pounds of P2O5, so that goes away. And if I'm trying to get just a pounds per acre, which is ultimately what I'm trying to do, to achieve that 50 pounds of P2O5, I have to supply 96 pounds of MAP per acre, 50 divided by 0.52. Now, I also have to account for the nitrogen that's coming from the MAP. So 96 pounds of MAP per acre is what I'm going to be supplying based upon my desired phosphate rate. I know that for every pound of MAP that I supply, I'm getting 0.11 pounds of actual nitrogen. So again, I continue to cancel out my units. And it turns out I'm supplying about 10.6 pounds of nitrogen per acre. Okay, so if my desired nitrogen rate was 30 pounds, I've got to subtract the 10.6 that's coming from the MAP. And again, I have this set up very similarly. Now remember, these don't cancel. The pounds per nitrogen per acre is going to be conserved. But I do know that for every pound of nitrogen, for every pound of urea that I supply, I'm getting 0.46 pounds of nitrogen. These go away. And voila, I need 42 pounds of urea per acre to achieve combined with the nitrogen from the MAP to achieve my 30-pound rate. Okay, and I apologize. I'm starting to move through this pretty quickly. Now I can do my blend calculation cost. This is fairly straightforward, fairly easy. If I know I'm putting on 42 pounds of urea per acre, all right, I know that it costs $340 per ton of urea. And I did this intentionally backwards just to maybe trip you up a little bit, but all you really have to do is pay attention to the units. The mathematical operation or the order of operation is really irrelevant. I just have to make sure that I get the right units. Pounds of urea go away, tons of urea go away. I'm left with dollars per acre, which is ultimately what I'm interested in. 42.2 multiplied by 340 divided by 2,000. It's $7.17 per acre to achieve that 30-pound. Again, considering that the MAP as well. This is just my urea cost on a per acre basis. The MAP, again, if you went back to the math, I was applying 100 pounds of MAP per acre. I know the cost of MAP in my assumption is $360 per ton. And I know I have to have my calculation to get rid of the tons. So the tons go away, the pounds go away, and I'm left with dollars. So 100 multiplied by 360 divided by 2,000, and it's $18 per acre. And I just realized I have the 96 and the 100 inverted. Dadgummit. This is why you should always triple and quadruple check these. The 100 pounds of KCl, this should ultimately be 100. That should be 96.2. And for that, I apologize. I'll fix this before it gets sent out to everybody. Pounds of KCl will go away. Tons of KCl go away. And again, this should be 100 multiplied by 360 divided by 2,000. This one should be 96.2. I apologize. I knew that I was going to make an error in putting these together. At least I caught it. So my total cost, if you're looking at a dry blend of these three products, is going to be $42.45 per acre. Now, just to make this a little bit more complicated, let's assume I'm fertilizing a quarter, 160 acres. How much of each product is required in the blend to cover all acres? So this is another level of complexity. Now I realize on a per acre basis, I'm putting out 42.2 pounds of urea. I'm covering now 160 acres. So again, you notice acre goes away. I've got pounds of urea, but I'm going to ultimately put this on a tonnage basis just for ease. And if you're blending products at a larger retail facility and you're not working on this like on my lawn or your front yard, you're probably going to be basing this on a ton basis anyway. I need a total of 3.38 tons of urea per field. Again, all my units went away. And this per field is just, you don't have to have this in here. I just kept it in here just for illustration purposes. 42 multiplied by 160 divided by 2,000. I need 3.38 tons of urea to go to that field physically to achieve my desired nitrogen rate when supplied with MAP as well. Again, this should be 96.2, not 100. But you're going to notice everything is the same. The acres go away. I'm just converting this on a tonnage basis, so the pounds of MAP go away. And I can't stress this enough. As long as your units match up correctly with what your desired end unit is, you rarely make a problem unless you forget to bring in the incorrect value like I did for this illustration. So I need 8 tons of MAP, and again, I will fix this before it gets sent out to the group. Do the same thing for the MAP. Again, that should be 100. But again, you're probably noticing the theme. All I'm really doing is taking care of units, and everything else pretty much takes care of itself. Here's the very last one. Boy, we're going a lot longer than I thought. And I thought that I would be, there's only 21 slides here. If you created a fertilizer solution, so I really want to illustrate this point because I see this mistake made very frequently when you're blending products. Specifically, if it's not blended at a 1-to-1 ratio. If you blend at a 1-to-1 ratio, it's really easy to calculate what the new nutrient analysis would be of the resulting product. And that's just simply taking the average. But when you start blending at different ratios, you can't just simply take the average of two products and expect that to be the representative nutrient concentration of the new product. Okay, so if I'm combining APP and 28 and the ratio is 1 part ammonium polyphosphate to 3 parts urea ammonium nitrate, what would the fertilizer analysis of this new product be? You actually have to employ something called the weighted average. And again, mathematically, this isn't complicated, but you have to make sure you're setting it up properly. So here's the illustration. If I want the new nitrogen content of this new product, I have to know what the nitrogen analysis is of UAN. That's going to be 28. We'll be plugging in actual values here in a moment. I multiply that by what the ratio of UAN is in this new product. So as I told you up here, I'm adding 1 part APP to 3 parts UAN. For APP, the nitrogen analysis is 0.1. The fraction of ammonium poly in this new product, its ratio is going to be 1. And then I have to divide all of this by the ratio of UAN plus the ratio of APP. So let's start plugging in some values. UAN nitrogen analysis is 28. UAN ratio is 3. I did this intentionally backwards so that I'm forcing you to pay attention to specifically what that 3 represents. And I did this as a 1 to 3. I did it backwards down here just so you, because sometimes people get stuck in this loop of, oh, whatever's first goes here. Order doesn't matter on this. You just have to make sure these things stay together. 28 is 3. And 10, which is the nitrogen analysis of ammonium polyphosphate, is 1, because in the ratio, it's 1 part APP, 3 parts UAN. For the UAN, you plug in that ratio, it's 3 parts, 1 part APP. Now it's just simply following the math. 28 times 3 equals 84, 10 times 1 equals 10. Make sure you do this properly. Okay, make sure you enter the equation. That's why I do this in a step-by-step process. 84 plus 10 is 94 divided by 4, 23.5. So the new nitrogen analysis of this product would be 23.5. If you just simply did the average of 28 and 10, you're going to be somewhere in the magnitude of 19. Because this is a heavier nitrogen product, your nitrogen concentration is going to be higher than that. Okay, that's another check. We're doing the same thing. I'm just going to change this to phosphorus. All of this is set up the same, except for instead of nitrogen, now it's a phosphorus basis. And actually, that technically should be P2O5. So there's 0 phosphate in UAN, so that's going to be 0 times the 3. The phosphate analysis of APP is 34 times 1. The 3 and the 1, similar to what we'd used before. You do the math. 0 times 3 is 0. 34 divided by 4, I get 8.5. So you can use weighted average. There's actually a way to set this up in Excel. It's called a sum product feature. But for simple blends, you can do this very, very easily. Just realize the more blends, the more material I put in the blend, the more complicated this math gets. It's not that the mathematical operations are difficult. I just have to make sure that this equation is set up properly. Just as far as conclusions, and I hope that I've impressed upon you that doing all of these are again, I don't like the word simple, but they're common fertilizer calculations that shouldn't be super, super difficult. I will never call them simple because there's a lot that you have to be aware of. If you're following your units and you're using dimensional analysis, hopefully you will take care of any of the issues that you have with regard to arriving at a improper solution. Because typically what will come up first is if your nutrients aren't correct, you obviously did something wrong. Track your units. I cannot stress that enough. I know we're running late. I know we only have this time for another 12 minutes. I didn't really see, I see the question from Melissa as far as the CEUs. That's something we're going to look into, Melissa. We will go in and see if we can ultimately file for CEUs for this particular webinar for this content. Stay tuned. We should be able to get that back to you pretty quickly. I'm going to give you a minute for a question if anybody has a quick one. Like I said before, I'm going to make the changes because I did screw up on a couple of those slides. I knew I would. I was getting confused, and part of this is I was doing other things while I was putting together this presentation. I'll get those all straight. The math wasn't wrong. It was just I was using the wrong values for the map and the KCL in that one example. This will be available for download for anybody who is here. We're also going to post this webinar somewhere online. Be looking for that link. Will we be sent a link for a download? Katie, I'm assuming that would be an affirmative.
Yeah, that's right. So we'll follow up with an email. We'll get this whole webinar has been recorded. So we'll provide a link to where you can rewatch the webinar, as well as you can grab the deck from Dr. Mullen as well. So just look out in your email for a follow-up.
And the only other thing is, if you do have questions, feel free to go to the eKonomics site and go to Ask the Agronomist. We do view those questions, and if it's specifically on this presentation, just note that in I suspect we should have some sort of an entry line at the beginning that discusses what this is in reference to. If it's related to this and it's related to the math, just let us know. We'd be happy to answer those. If you would like to see this series expanded and talk more about liquid products, again, it's another level of complexity. We'd be happy to do that as development of additional content. For all of you who attended and stuck with us to the end of this, I appreciate your time. I hope that this sort of helps you with the execution of your job, specifically if you do have to occasionally do these calculations, gives you a comfort level with approaching these. I know in my interactions with agronomists and undergraduate students, math is never something that we're a fan of. I was always the geek. I love math. Maybe we should do a series on integration and the importance of it in agriculture. We won't do that, by the way. That will never happen. If you're interested in calculus, go to YouTube. There's some great channels on doing calculus calculations. and actually making it understandable. But I hope this just makes it easier for you when you're executing your job and you're not so intimidated by these math problems that we're presented with. These are, again, not simple. They're fairly straightforward. So Derek has a question. Are there calculator tools we can use online? That's a really good question. I don't know if there's a downloadable link. Again, I have some that I distribute internally. Part of the challenge that I have with distributing those broadly is I have to institute a lot of controls because I work in an Excel environment. We don't have the capacity to make a standalone executable file that would do the math. My suspicion is there are probably some apps out there that probably do this. I haven't looked. I feel like I have in the past, but I don't know what I had arrived at. But that's a really good question. If you really want one, and I know what's going to happen when I put this out there, if you really want one, go to Ask the Agronomist and request it, and I will send you one that will do all of the math that I have done here, but it will do it automatically. And again, I have sent that out primarily internally, but now that I think about it, I have sent it to some customers as well. And thank you, Melissa, for the plug. The only other thing that I will mention is if you have not been to the economic side, and everybody has, obviously that's here, please make sure you're going and checking out those ROI calculators, our nutrient removal calculators. We're hopefully going to be adding nitrogen here. Boy, when I say these things out loud to an audience outside of my team, I get really nervous. I'm going to put the pressure on us now. We're going to start attempting to integrate some nitrogen ROI calculators. That's a whole other level of complexity, but we think we can get there probably in the next 6 to 12 months. So just be keeping an eye on those ROI tools. We do update those as frequently as information is available. We're also going to be adding sulfur removal to our nutrient removal tool. So just be on the lookout. We're always updating the site. There's always new content there. Please feel free. And if you have any questions, ideas for content, do not be afraid to hit that Ask an Agronomist button to interact with us and help us with the content, because ultimately who we're trying to service is our customers, those that work in the retail space. Thank you so much for your time. I hope everyone has a great growing season, and we will look forward to talking with you all next time. Take care, everyone.